Hi, my name is Nadya DeBeers and I'm the head maths teacher at English Trainers. Today I'm going to be going over question 16b, part 1 and 2 from the 2018 HSD Extension 2 Maths exam. Alright, let's get started. Alright, so in this question we have two parts. Part 1 asks us to prove that length dy is equal to length ZE, and in part 2 we're asked to find the exact value of the ratio YZ on BC. Right? So we're going to start with part 1, but before we get into that, let's talk about what's given, or what information is provided. So in our triangle, we know that length AB is parallel to IH. We also know that AC is parallel to GF and that BC is parallel to DE. Now we also know that AB on IH is equal to root 2, AC on GF is equal to root 2, and BC on DE is equal to root 2. So before starting these types of problems, I always find it's helpful to write down what's given, just because seeing that information in your own handwriting can sometimes make things click or make it easier for yourself later on. But anyways, we'll come back to that information later when we need it. Alright, so the first step in proving that dy is equal to ZE is going to be to show that triangle BFG is similar to triangle BAC. Now, it might look obvious, but it's always important to actually state why these two triangles are similar. And of course, in a problem like this, it's mandatory. So we can start off by saying that both triangles have angle B in common. So we say that angle B is a common angle. Now, the next thing that we can state is that angle BGF is equal to angle BAC. Since GF is parallel to AC, which is given, this means that those two angles are corresponding angles of parallel lines. And for the exact same reason, we can say that angle GFB is equal to angle ACB. Now by angle, 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 we can deduce that triangle BFG is in fact similar to triangle BAC. Okay? And now, going back to that given information in the start, since we know that AC on GF is equal to root 2, we can also say that BC on BF is equal to root 2, since triangle BFG is similar to triangle BAC. Okay, and if that doesn't quite make sense, the reason is that AC on GF equaling root 2 is the same thing as saying the length of GF, when we multiply that by root 2, we get length AC. Since BGF is similar to BAC, that means that that common ratio is going to be true for every pair of side lengths that we're working with here. So, by that logic, we can say that BC on BF is also equal to root 2. Alright. Let's show that triangle HIC is similar to triangle BAC. We can say, to prove that this is true, that angle C is common. They both share this angle. We can also say that angle IHC is equal to angle ABC, since, once again, BA is parallel to HI. Thus, those two angles are corresponding angles of parallel lines. And by the same logic, we can say that angle BAC is equal to angle HIC. Once again, by angle, 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 we can deduce that triangle HIC is similar to triangle BAC. And once again, since we're given in the start that BA on HI is equal to root 2, we can also say that BC on HC is equal to root 2. We have these two equivalencies, right? We have BC on BF is equal to root 2, And we also have that BC on HC is equal to root 2. Since they're both equal to root 2 on the right-hand sides, we can go ahead and equate the left-hand sides, leaving us with BC on BF is equal to BC on HC. Now, by a bit of cross multiplication and cancelling, we can see that HC is equal to BF. Okay, so now that we've shown that HC is equal to BF, we'll box it, and we'll come back to that later. So now, step 4, let's look to the parallelograms within our image. So you can see, I'll highlight them here. We have pairs of parallel sides, right? Since we know that AB is parallel to HI, that DE is parallel to BC, and FG is parallel to CA, you can see that by definition of parallelograms that DYHB and ZECF are both parallelograms. Now, by definition of a parallelogram, we know that they have opposite equal side lengths. Okay? So we can then conclude that BH must be equal to DY and ZE must be equal to FC. Alright, so this is the fun part. This is where we get to put everything that we've just solved and figured out together into one piece. So from part 3, we know that BH is equal to FC. And from part 4, we've determined that BH is equal to DY and that FC is equal to ZE. So what we can now say is that BH, which we know equals DY, which we also know equals FC, which we also know equals ZE, is all equal and true. Thus, we're able to say that DY is equal to ZE. So that's part 1. We've proven that length DY is equal to length ZE. Alright, in part 2, we're asked to find the exact value of YZ on BC. We'll do this by looking at what we know and what we figured out from part 1. So I'm going to draw a picture here so we can reference that, and I'll try to keep it color-coded so it's easy to see. We'll start off by saying a fact that we know, and that is that YZ is equal to DE minus DY minus ZE. And we know that's true by just looking at the picture. The reason I'm starting with this is since we're asked to find the value of YZ on BC, I know that I'm going to want a YZ on the left-hand side of my equation, so that in the end, we'll hopefully have BC's on the right-hand side, and we can divide by BC in order to have our lengths on the left and numbers on the right. Okay, so that's the logic for the starting point. So we have our YZ on the left, and now we need to make sure that we have only BC's on the right-hand side so that we can factor those out later. So from part 1, we know that length DY is equal to ZE, since that's what we were after proving. So we can go ahead and substitute our DY's in for the ZE. So we now have YZ is equal to DE minus 2DY. Now since DYHB is a parallelogram, and we know that DY is equal to BH, we can say that YZ is equal to DE minus 2BH rather than DY. Now, since it's given in the beginning of our problem that BC on DE is equal to root 2, that means, by a bit of algebra, that DE is equal to BC on root 2. So we'll substitute that in for DE, and we now have YZ is equal to BC on root 2 minus 2BH. Now, from the picture, we can see that BH is equal to BC minus HC. So we'll substitute that in, and we now have YZ equals BC on root 2 minus 2 times BC minus HC. From part 1, we discovered that BC on HC equals root 2. Thus, once again, by a bit of algebra, we can say that HC is equal to BC on root 2. So we'll substitute that in, and we're looking at YZ is equal to BC on root 2 minus 2 times BC minus BC on root 2. So we have our YZ on the left, we have all BCs on the right, we're exactly where we'd like to be. Now we just need to do a bit of algebra. So we'll factor out a BC and we're left with YZ equals BC times 1 on root 2 minus 2 plus 2 on root 2. And we mush it all together and we're left with YZ on BC is equal to 3 minus 2 root 2 on root 2.